What did one hat say to the other? You go on ahead. All right. Let's go to our next topic, which is differentiability. There we go. So differentiability is basically, we're going to be able to try and prove whether something is differentiable or not. And the way that we do that is by kind of like checking that it's smooth and continuous. Now, we talked about continuous last lesson. We're going to actually apply it in this one. So long story short, not all functions are differentiable everywhere. Okay, there's certain points, and we saw, for example, you can't differentiate. I'll explain why. Differentiating means you're finding the gradient of a tangent. Okay, now when you draw a tangent, you can only really draw a tangent on a part that's smooth and it's continuous. You can't draw a tangent at a discontinuous part, and you can't draw a tangent on a pointy part. So if TLDR, if it was too long and you didn't read it, if your function is smooth, it is differentiable. Okay, smooth equals differentiable. Now, if I have these two graphs here, what you'll note here is at this point there, that is a point. It is not smooth, so it's not differentiable. Okay, so because it goes to a point, it is not differentiable. It's differentiable everywhere else. So I can differentiate all the way down here, all the way down here, just at that point. In this particular case, when x equals to 0, and this is the y equals absolute value of x graph, by the way, it's that x is not differentiable at x equals 0. Let's do that. Okay, because it's not smooth at that particular one point. Same for this one here. You can see that if I was to do this, you can see that there's an asymptote right down in between these two. So we say that this function is not differentiable at x equals 0. But then there's also, let's say if I labeled this as something like, I don't know, 5, we also say it's not differentiable at x equals to 5. So let's just do that. Okay, so we can see that everywhere else, this is smooth, so it's differentiable all the way here. It's differentiable from here to that point there. And then it's differentiable from here to there. Okay, because it's all smooth, 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 except for the break here and the break here and that point there. Hopefully that makes a bit of sense. Now, a question may look is they'll say, prove that a certain function, and this is a piecewise function, prove that it is differentiable for all x. Now I'm just going to fix this question. That's what it's missing. So let's take a look. First thing that I would do is I would probably do a quick little sketch. And we can see here that the point of interest, that there's something that happens around the point x equals 1, right? That's kind of where there's a change of value. So I'm going to do a quick sketch. And I know that something happens at x equals to 1. Okay, on the left-hand side, when x is less than 1, it's x squared minus 1. So it's actually going to look a little bit like that. And I cannot equal 1, so I'm just going to do that. But then the other one I have is I have 2x minus 2. And so it's going to cut at minus 2. But it's kind of, we're not going to care about this part here until we reach here. It'll be a nice little straight line, and it's kind of going to go this way. Okay, so first of all, we can kind of see that it is part A. Is it smooth? Do we have any points? Yes. And then the second thing that we need to sketch, or that we need to figure out, is it continuous? And the answer is yes, because they meet at the same point. Okay. Now, another way that we can check whether something is smooth, and if I just make a bit more room here, is I need to find the gradient of the tangent. Okay. Let's take a look at the gradient of the tangent. So if I'm looking at this gradient of the tangent, let's look at both of these. So I have fx equals x squared minus 1. So that means my f dash x at this point will be 2x. Now at the point at x equals to 1, my gradient of my tangent now becomes 2 times 1, which is 2. If I'm looking at my other function, I'll have f dash x, fx. Let's go. Fx equals to 2x minus 2. And then if I differentiate this guy, it gives me 2. And so we can see here the gradient of my tangent would also be 2. So if you can see here, gradient of the tangent is the same. Okay, and now again, I can prove the continuous one algebraically as well. I'd say, okay, what is, if fx equals to x squared minus 1, let's see what f of 1 is, because that's where the point of interest is. This would be 1 squared minus 1, and that would just give me 0. But let's check our other one. Our other function is fx equals to 2x minus 2. And again, f of 1, which is the point we care about, would be 2 take away 2, which is 0. Therefore, also continuous. Okay, so it's up to you whether you want to go about it graphically. I would prefer graphically, so that way it means that you actually understand the graph. But then there's also the second option of we can actually prove it mathematically and using calculus and some substitutions to prove continuous and smooth. Okay, so don't forget, prove something is differentiable, you just need it to be smooth and continuous. That'll do it. Hope that helps, and I'll catch you guys in the next one. See you later. Bye.